What are the challenges of training artificial neural networks? Have you ever wondered what it takes to train artificial neural networks? It's not just about feeding them data and letting them learn. There are several hurdles that developers face along the way. Let's break down these challenges to understand them better. First, let's talk about data quality and quantity. Neural networks thrive on large amounts of high-quality data. However, gathering enough labeled data can be tough. In fields like medical imaging, privacy concerns, and the cost of labeling data can limit what is available. Additionally, if some classes of data dominate, it can lead to biased predictions. Overfitting is another issue where a model memorizes training examples instead of learning from them. To combat this, techniques like data augmentation, which involves rotating images or adding noise, can be useful. Regularization methods, such as dropout, also help but requiring careful application. Next up is optimization challenges. Training these networks means adjusting millions of parameters to minimize error. Problems like vanishing gradients, where updates become too small, and exploding gradients, where updates become too large, can stall or destabilize the learning process. These issues are especially common in deep networks that use certain activation functions like sigmoid. Alternatives like rectified linear unit activation and normalization techniques, such as batch normalization, can help manage these problems. Choosing the right loss function is also critical. If it does not match the task, it can lead to ineffective training signals. Now let's discuss hyperparameter tuning. Neural networks come with many hyperparameters, including learning rate, batch size, number of layers, and neuron counts. Finding the right combination is essential for good performance, but it can be time-consuming and costly. Making poor choices can lead to slow convergence or overfitting. When it comes to reinforcement learning, additional challenges arise. The dynamic and non-stationary nature of learning targets can make it hard for the network to converge. Value estimates may oscillate or diverge, complicating the training process. Moreover, data collected sequentially is often highly correlated, which violates assumptions of many training algorithms and leads to inefficient learning. Techniques like experience replay, which randomizes training samples, and target networks can help improve stability. Lastly, let's touch on dynamic neural networks and hardware compatibility. These emerging networks adapt their computation based on input, creating mixed discrete continuous optimization problems that are harder to train. They also reduce parallelism, which can decrease efficiency on graphics processing units designed for static computation graphs. Designing hardware-friendly dynamic models and compatible hardware remains a challenge. Combining these models with techniques like quantization and pruning may improve efficiency. In practical applications, such as artificial intelligence tools like ChatGPT, DALL-E, and Midjourney, these challenges significantly influence how well models understand language, generate images, or respond to user inputs. Addressing data limitations, ensuring stable training, and optimizing models for available hardware are essential steps in developing reliable and ethical artificial intelligence systems.